next presentation comes from Dr. Jan Goetz.
All right, thank you for having me here. For me, this is still a little bit, let's say, unknown territory because I don't have a background in high-performance computing. I'm a physicist, quantum physicist, and I've started a couple of years ago together with 3 other co-founders a company that builds quantum computers. But what I want to achieve here is actually building bridges, because I think the 2 communities together can actually achieve quite a lot. And this is also the philosophy of our company, trying to merge quantum with high-performance computing. And one way to do this is, of course, start playing together. So you put your toys into the same sandbox and start playing together. And this is what you see a little bit illustrated here. Also in this picture, it's kind of a rendering of a big computing center and then the quantum computer there. And I will also show you a few projects where we're actually doing this and trying to find out with the community how can actually quantum computers work together with HPC environments. So the way I've structured the presentation today is that I wanted to give you a brief intro into the company, because I think also not everyone is familiar with this concept of kind of doing this entrepreneurial move and spinning out a company from an academic environment, what we did there. So I have a few slides on this. Then a little bit how we think about this kind of quantum computers working as accelerators in HPC environments, and then talk a little bit about what do we need to make it happen, algorithms, the hardware, and then of course the software integration part. And then I will show a few example projects where we are working in this field. All right. So as said, IQM, it's a company that's a spin-out from Aalto University in Helsinki, so the physics labs there. Mikko was the professor. I was working with him for a couple of years doing experimental quantum physics. So the labs, they look like this, so lots of kind of electronics and devices there that we characterized, and Mikko always had this dream to maybe at some point start a company and commercialize the technology that was developed in the lab. And the thinking here was really from the beginning that we wanted to build a big European player that can compete on a global scale. So in the field, if you're following it a little bit, you find really big names like IBM, Google, Huawei. They're all having efforts of developing their own quantum computers. And in Europe, typically we have this challenge that there's very little efforts of, let's say, big corporates building computers. We don't have it so much anymore. And this was a little bit the idea here, really create something that can play kind of in the same field with the big ones. But of course, we are kind of very humble, and we started in the physics lab. So actually my first duty as a CEO of the company was to buy this kind of IQM Nest thing here, which we just put on the wall, because at some point we had to start pitching to investors, and we had to show them that we have something real. And of course, when in the very beginning, the only thing you have is basically the lab and the technology there. So this is kind of how it worked. And then we brought the investors there into the university and said, look, this is the beginning, but if you help us, we will make something big and industrial out of it. And then, of course, something that in academia is usually not so well known is that you need to kind of then start the business plans and really think about the logic and is there actually business to be made. And we had a person, former chairman of Nokia, visiting us and said, well, you really need to do this, but you need to have a business plan. And then but you know how people in physics works, they kind of they think in orders of magnitude and make sketches, and then if it works out, it's fine. So this was our very first business plan here. So we just kind of summed up what do we need, and we thought, okay, we need something between 8 and 15 million to get started with a company. And the average is 11.7, and actually we then raised 11.45. So and this is kind of the approach in physics. You just sketch something, and then if you're lucky, it works out in the end. But of course, then you need to have a little bit more detailed plans than this at some point. So this was our second business plan that we created, and you see already much more technical detail in there, and it's much clearer actually what we wanted to do. So this is what was created among the founders in Hoplop in Espoo, which is a city in Finland. And if you're wondering, okay, why Hoplop? Of course, we all had our real jobs still in parallel, and some of the founders actually had quite a lot of kids, and Hoplop is actually an amusement park for kids, so we were kind of sitting there developing these plans. And this is this kind of startup entrepreneurial mindset that you sometimes need to have, just do things, and then if you really push for it, you will make it happen. And what then came out of it in, let's say, 4 to 5 years is now a company which has around 300 employees. We really are still on our mission to build full-stack quantum computers. We have built our own fab in Espoo, and we have started actually selling and installing them also in several cases. So what we actually offer in the end are, we focus very much on the hardware. So we have the Radiants, which are the larger scale quantum computers. We have a smaller one, which we call Spark, for educational purposes. Then we also have connected our quantum computers to a cloud if you just want to play around with it. And then we have an educational offering on top of this. So this is roughly what we offer as the company. And then, of course, being a startup means behind the doors, it's all a little bit hectic and chaotic, but also a lot of fun. So this is kind of how we are then, of course, also motivating and getting the best people into the company. All right, so this is a little bit the story of what we have been doing, but then on a more serious note, so on kind of the way we see it working, also together with this community, is really to start integrating it. And we see this actually coming in stages. So the first one is just having a quantum computer somewhere and then a remote access, and you can start executing some algorithms, you can play around with it, get to know how it works, and maybe you believe that this is something that will come. But actually, the second part then is really start bringing the systems together, and this is something that we have now also started executing. So really bringing the quantum computers into an HPC environment, checking does it work, are the kind of the vibrations okay, are the electromagnetic disturbances okay, how does it work on the software stack, how do we need to train the people to keep it running, all of these kind of, let's say, rather simple problems also need to be solved there as well. And then the kind of the vision going forward is that we really kind of have an on-node integration, bringing those systems really kind of together. The first two, as I said, we are already executing this kind of on-node integration. This is still something where we are in the R&D phase and discussing how this could actually work out in the long term. And as said, we want to be an active part of the community. So if you're interested in kind of trying to do something with us, our technical teams, our researchers, we're always very kind of welcome to do so. This is here just one example which we did with people at LRZ, really conceptualizing how we can bring quantum and HPC together. And we are very much interested actually in developing these efforts also forward and trying to find out what's possible and also, of course, what is not possible and what doesn't make any sense. When you think about how can quantum and HPC work together, there are different approaches that we are discussing. One is just offloading the workflow. So basically you just give some of the tasks, let's say the ones that fit from a mathematical point of view, the more complex part to a quantum computer, and then merge the results. There are these iterative approaches as well in hybrid algorithms. These are all kind of still active fields of research, and people are investigating actually in which of these configurations would there be a real advantage and maybe a speed up ultimately, and what is the best way of bringing those two worlds together. All right, but this is kind of our approach, really trying to bring these approaches together and see what's possible. But then on the quantum side, what we do is we work on algorithms and think about how to connect them to use cases. We do a lot of hardware, obviously, and then also the software integration. So on the algorithms, and I will not give you a deep lecture, but basically we are still looking at this very much. If you look at this kind of schematic here of a quantum circuit, it's very much to kind of machine coding. So you have qubits, which are here represented as these lines. And in our case, these qubits are actually on a silicon wafer. These are nonlinear LC circuits. So it's a kind of a circuit on a silicon wafer which has a certain frequency at which it operates. And then a 1 qubit gate could, for example, be a bit flip. So you start in the 0 state, there's nothing in there. You apply a microwave pulse at this frequency, and then you bring one quantum of energy in there, and you bring it to the 1 state. And the clue is, if you bring exactly half of this energy package in there, it doesn't go to the 1 state, but with 50% probability it goes to the 0 plus 1, like the superposition state. And this is one of the quantum resources that we use, is that the qubit can actually be in these superposition states between 0 and 1. And only if you measure at the end, actually, you will see, now, was it a 0 or was it a 1? So then it has to decide, is this Schrödinger cat example. So we can apply these 1-qubit gates and make bit flips, but actually we can also do 2-qubit gates, C-knots, for example, by bringing then 2 of those qubits on the chip in resonance and entangling them, and then they share information. And the clue is actually the way you can think about it more from a mathematical point of view, that a qubit in the mathematical representation is a 2-by-2 matrix, and if you entangle 2 qubits by applying these gates, basically you have a matrix multiplication there, so it's already a 4-by-4, and then the third qubit is an 8-by-8, and this is the way it goes. And this is the way then you can construct your algorithms in there, by applying then these matrix operations in there. And then in the end we measure, but it's not kind of it's a probabilistic thing. So we have to repeat the same algorithm many times, of the 1,000,000 times or so, and then we get a probability distribution. So assume that this algorithm here, or these 3 gates, they would produce a state where the first and the third qubits are flipped, and the one in the center is still in the 0 state. Still, we would measure, in many cases, something else because of the noise that's in the system. But then we say, okay, clearly here's the peak, so this is our answer. So this is roughly how it works, and the clue is then, from a mathematical point of view, is that there are certain problems which scale much more favorable in this scenario compared to the normal binary logic, and basically this is what you see then here, is that as a function of problem size, in certain cases the quantum solution can scale linear in the runtime, whereas it would be exponential then for other problems. So that's the kind of level of quantum I will give you here. If you're interested, I highly recommend you to go and check out our online, it's a free online platform, IQM Academy, where you can get a deep dive into all of these concepts and how it really works. And basically, so on the algorithm side, this is something, if you look now at our stack, that we are investigating. We are actually actively developing algorithms, and then we are partnering with many other companies and startups, trying to think about how they can then build these use cases around it. But just to give you an understanding, I brought you some examples. Since this is HPC AI, I took some examples from this field. Maybe we skip this one. 2 here, one is quantum kernel estimation. So you use a quantum approach for kernel estimation. And there are ideas how to speed it up. And basically, you use their basically the quantum state you compare to reference states, and then you can apply it to this. There are also concepts in quantum neural networks where you use as input you need parameterized quantum circuits. The challenge there is a little bit the second point, that usually you have larger data sets, and that's actually something where quantum is not good at all. So you don't get a lot of data through these processors, and this is for us, for example, one of these examples where would go well together with HPC. So you would have some pre-processing, and then only the distilled problem will go into the quantum computer, and only the mathematically complex part is solved. And then the third one is quantum reservoir computing, where you basically use the huge Hilbert space, so this huge matrix space that spans out there, when you apply the concept onto the reservoir computing approach. So just to give you some ideas, so there are many of those also then beyond machine learning and chemistry and optimization and the like, where you find quantum approaches applied to known algorithms. And we're doing this in an exploratory phase. These are just some examples. Not all of them are machine learning, but for example, the second one there with Siemens, this is about reinforcement learning. So we are basically working here in a proof of concept phase. So what we can do in these examples is we can say that it works on a principal level with a quantum computer, but it's not yet outperforming any supercomputer by far. But basically the idea is that for those companies it's important to understand where does it work, and then assuming that at some point there is a large-scale quantum computer, they can actually apply it to their problems. So we do this in a couple of cases, as you see here. We also have some on partial differential equations, which go into climate simulations, trajectory optimization. So just to give you a feeling where the industry is actually looking at, and where we are trying to provide some answers of what can be done and maybe what cannot be done. All right, so this is kind of all still in the exploratory phase. As said, nothing of this, what I've shown you, works on a commercial scale that someone would make money with it, but they want to get quantum ready and they want to prepare themselves. But the underlying thing is always that you have a quantum computer, and in particular then the quantum processor, and this is our core competence, is really building the hardware. We see ourselves as a system integrator, so if you open up these big systems, it looks something like this, and you see this often also if you just Google quantum computer, these golden chandeliers. What you see here is these horizontal plates. These are just different temperature stages. So the lower you go here towards the bottom, the colder it becomes. And actually, the processor is inside these kind of magnetic shields where it's only a few millikelvins, so a few thousandths of a degrees above absolute zero, so much colder than anywhere in the universe, actually. And we need these low temperatures to freeze out all the electromagnetic noise and all the other stuff and really to observe the quantum effects on the chip. The chip, as said, is then inside these magnetic shields. You see all the cables. This is where we bring these microwave control pulses in, for example, to do the bit flips or the C0 gates and the like, and also then the signals travel back up, and there's lots of room temperature electronics, then high-frequency electronics to do the classical part of the computations. The core of the quantum computer is the processor, and this is mainly where we are working at. So we are designing the processors with our design tool. Then as I said, we have our own little chip factory in Finland where we are producing the silicon wafers. Then we cut out the processors, we package everything, we act as a system integrator where we buy a lot of electronics and components together, and then we do the software integration to a certain extent as well. This is how the processors look like, and you can think of us from an innovation perspective similar to a company like Intel. Like every year or so we bring out a new processor generation and they become better and better over time. So our first processor was the 5-qubit chip. Actually here you even see these kind of structures on the chip, the qubits. You can see them with your bare eyes. They're like 100 microns or so in size. The 20-qubit chip that we have here, you already don't see anymore the structures because we put a flip chip on top of it to protect the circuits. The 54-qubit chip, you see already many more lines coming in. We have actually now, this is not yet a real picture, but we have the first 150-qubit chips already also produced, and they will be available quite soon. And then, just to give you a feeling, then, for example, if you go to our cloud offering, you see some specifications for those who are a little bit more into the field. Usually the important numbers are these so-called fidelities. So how well does the processor actually work? Because the biggest challenge is still the errors and the noise that you have in the system. So here on our 20-qubit chip, for example, we have a median 2-qubit gate fidelity of 99.5%. So this means if you apply 100 2-qubit gates in 99.5%, it's the correct outcome, and then this 0.5%, actually there was an error, which is at the moment the limiting factor, and what people are looking for are error correction and error mitigation methods then to really bring the error rate down so that you could apply at some point millions of gates. Because now if you apply thousands of gates, basically there's only noise left then because of those errors. But this is roughly where we are with our systems, and you can do nice kind of proof of concept experiments there. You can run algorithms and you get meaningful results out. Maybe for this community, one topic is also always the kind of the energy consumption and what does it actually mean for quantum computers. We are part of a group that's called the Quantum Energy Initiative, which try to give from a more scientific perspective answers to these questions, because it's still a field of active research. Nobody really knows the answer, what's the exact energy consumption of large-scale quantum computers, which maybe have millions of qubits or so. But we are working on it, and here are many numbers. You don't need to look at all the numbers, but basically we are working on these kind of energy budgets and what does it mean. At the moment, just to give you a feeling, these are we need for our 54-qubit system around 30 kilowatts of power. But the question is, how does this scale if you would have a 1,000,000-qubit quantum computer, for example? And that's still a kind of active field of research, and hopefully a lot of innovation still can there help actually bringing down those numbers. Another thing is actually the execution speed. Even though if you assume to have speed up with a quantum computer over a conventional computer, the question is how fast is the system, and there are actually still different platforms out there to build quantum computers, and we are using this superconducting approach. Another, maybe the kind of other widely known one are the so-called ion traps, and this is just to give you a feeling why we think that superconducting will actually be the solution on the long term. Is that the speed of execution in our case, or let's say single gate operations, is on the nanosecond regime. And then if you think about, you want to have millions of gates and you want to average over it, actually these times add up still significantly. And for example, in the ion traps, they are 3 to 4 orders of magnitude slower, and this is then what you would see in the end. So from this perspective, if you think about this wall clock time, I think how it's called in this community, I think the superconducting systems are the ones that will really then be the solution on the long term. All right, so we have some algorithm ideas. We know how to build quantum processors, and of course, then we need to make it work somehow, and we need to give people the opportunity to work with this. And this is something where we are still kind of also adapting to the needs of different groups, because researchers, they want to basically have a full control over the system all the way down, have pulse level access, play with the compilers, all of this, and they want to basically have as open systems as possible. The industry, they just want to play with it. They want to use their algorithms that they know, submit a job and have it executed, and then see whether something meaningful comes out or not. And then our experience with the HPCs is basically they want to have a good integration into what they're currently using, and the seamless and lightweight integration there. And we're trying to adapt to all of those by building a software stack for our computers that is quite flexible, and that adapts to all of those needs. So we do have a very experimental access to our systems, which is very open, and you can play around with thousands of parameters if you like. But then we have also more straightforward approaches using actually then third-party solutions. So Cirq is the Google software platform, Qiskit is the IBM, and then we do have a few others out there as well. We are working also with NVIDIA on a CUDA integration and the like. What we do with on the HPC side, and this is mainly with the LRZ and Garching, is actually think about how to bring it into the HPC environment, for example, for this kind of Slurm and other approaches. But this is, as said, these are still ongoing developments, and if someone is interested in working in these fields with us, we are very actually open to collaborate there and learn also from your community what's possible and what should be done. All right, so to finish up, just a few examples so you get a feeling of what we are doing and where. We have actually announced recently that we will provide a small system, one of these Spark educational tools, to the Jülich Supercomputing Center. They're actually very advanced when it comes to the adoption of quantum computers. They're also working with a few other systems over there, and we are really looking forward to put then our system there and see how it compares to the other ones. We have in Finland, we have an ongoing project with VTT, which is the National Research Center there, and they're hosting 20 and a 54 qubit system from us at the moment. And this system is actually remotely connected to LUMI, which is more in northern Finland. VTT is in Espoo in the headquarters, but we do have a remote connection there between LUMI and Helmi, how the quantum computer is called. So this is kind of the first step that I showed you on our vision side, is this kind of remote connection between a quantum computer and an HPC. But then actually at LRZ in Munich, we are really working on bringing the systems physically together. So this is a picture taken some time ago already, where we are building our system actually, and this is the hall where the LRZ supercomputer is. So this is the ongoing work there. You see actually how our system is being delivered here to the LRC supercomputing center, and we are super excited about this one, and we really want to push these kind of activities forward. And then we have a smaller project ongoing at Barcelona Supercomputing Center, where we are actually supporting a local effort with our processors. So we are not building there the full system, but we are providing our processors for the quantum computer that's being installed there in this nice chapel hall that they have. And then nowadays, of course, nothing works without NVIDIA, and this is a work that we are actually quite actively trying to push forward, is bringing our quantum computers together with their CUDA quantum approach, because this is very aligned with our way of thinking that in the future you would have different kind of accelerators probably, and then some kind of orchestration, and the algorithms are being then fed into those platforms that are best suited to solve the problem. All right, so that's a little overview. I'm here with two of my colleagues, so if you have any questions during the coffee break, please reach out to me or Cosma and Ulrich, who are somewhere here in the audience. And of course, we are happy to answer any questions and get into an active dialogue together. So thank you.